Am I audible? Can anybody respond?
Yes, sir.
Are you able to see my slide?
Yes.
Okay. So I think the speaker has not joined till now. So I think there is some issue. I am trying to connect him. I'm trying to connect him, but he's not available, I think. So let me start today's session. So in today's lecture, we'll discuss about role of fog-empowered vehicular ad-hoc network in 5G network. So I think my screen is visible. Can anybody respond? Okay. So let us start. So as you can see in this title, we are talking about three different technologies. One is the fog computing, another is the vehicular ad hoc network, another is the 5G network. So it is a typical application of, you can say, integration of these three technology, and especially we have applied these three technologies in the field of vehicular ad hoc network. So fog is a technology which is near to the cloud. Fog devices are near to the cloud, and it is a complementary, you can say, technology. It is not going to replace the cloud, but it is a complementary for the user, because user can get the faster services in fog computing. But if you need a larger computation, you have to depend on the cloud. Similarly, due to the popularity of smart cities and smart transportation or smart healthcare, one of the such implement is called as vehicular ad hoc network, where we need an intelligent transportation system. In intelligent transportation system, we mostly deal with various vehicles. We deal with the roadside infrastructure and how we can get services or can provide services using the vehicles. So in this talk, we'll discuss about these are the some of the topics that we are going to discuss, or you can expect these topics in this 2 hour to 3 hour session. So I'll tell you about the requirement, the individual advantages of each and every technology. That is fog computing, vehicular ad hoc network, and the 5G network. Then we'll discuss about the integration of these three technology, and after that we'll discuss about various device association techniques. So device association techniques are generally used to connect the vehicles with the roadside infrastructure. So a vehicle can be connected to the roadside infrastructure using appropriate signal, or it can be connected based on the quality of service, or it can be connected based on the favorite content. So we'll see there are three different type of association technique, and in fact we are focusing on one of the device association technique, that is signal over technique. So next is we'll see one of the two different problems we'll discuss, research problems. One research problem is related to RSU, that is roadside unit, in which based on the reachability of each and every vehicle to a particular fog node, the signal strength is increases and signal strength is again decreases when you away from the mobile tower. So based on that, we have two different technology. One is called as RSU based resource scheduling. Another is revenue based service management, which is an improvement over this RSU based resource scheduling. Then we'll discuss another research problem in which a large area is divided into multiple grids, and one grid may be overlapped with another grid. So vehicle may be present explicitly with a particular fog node, or it may be available in the junction point of the two fog node or overlapped region of the fog node. So in that, vehicles can get service if it is present in a overlapped region. So they can get service either from the first fog node or they can get from the second fog node if it is overlapping region of two fog nodes. But if it is available only in one fog node, then explicitly that fog node can provide the services. And if the particular fog node is exceeding the capacity, then the vehicle is not going to get the service. Similarly, you can say in context with this particular problem, we want to improve the service capability and the serviceability. We want to improve the throughput. We want to improve the resource utilization. These are some performance metrics where we can look into. So in order to solve this particular problem, we have three different algorithms. One is dynamic resource orchestration algorithm, another is signal aware algorithm, another is dynamic resource management algorithm. And this dynamic resource orchestration and signal aware algorithm is a hybrid algorithm over the previous two algorithms. So dynamic resource orchestration plus signal aware. So by combining these two algorithms, this algorithm is developed. That is a hybrid algorithm. And we have done improvement over this dynamic resource management and the signal aware algorithm, that is called as dynamic resource management algorithm. Then in order to implement these set of algorithm, we have certain setup and results. Okay, so in the simulation we have set of simulation parameters that we need to focus how to implement these algorithms, and we will see the result part. So let us see why this is important, why this problem is challenging, what are the things where people concentrate on, what are the problems that people have seen in this particular architecture, and how to solve it. Nowadays, we know that IoT is a very popular platform, right? Every day, multiple devices are connected with the Internet of Things. Previously, we know that only very few devices are having sensors. Now, almost all the handheld devices are having sensors. So, number of devices having sensors, and they have capability to connect with other devices. Machine-to-machine communication is possible. They can connect with the cloud. They can exchange the data, and they can do a lot of things. So, with the advancement of IoT paradigm, so it is possible to visualize a smart city or visualize a smart transportations. In fact, a smart city, smart transportation case, IoT devices play a major role. For any type of improvements or any types of device in which you want smartness, nowadays we are putting various IoT devices. But if you look into these devices, like if you see this particular diagram, we have a computer, a personal computer, we have a smartphone, we have camera, we have iPad, we have, we can say, we have various applications, or we have smart vehicle, we have smart key, we have smart transportations, smart communication. All these are associated with the devices are connected to the cloud. So anything you want to process, so everything need to be processed. Anything you want to do processing, storage, every devices is connected to the cloud, right? But if you see the cloud data center, especially if you look into the cloud data center, they are generally very far away from these handheld devices, right? So as they are very far away from the devices, latency becomes one of the major issues. And these are heterogeneous devices because their computation power is different. Like if you talk about a vehicle, its computation power is quite more in comparison to a smartphone. If you talk about a camera, camera power is very less in comparison to the smartphone. So these are the set of heterogeneous devices. They are connected to the cloud. So in order to realize smart city or smart transportation, we need to integrate all these objects or devices which is of heterogeneous nature. And some popular protocols which we are using to connect with one system with another or multiple system, they are Zigbee, Wi-Fi, Bluetooth, long-term evaluation, and 5G. Now we are using VoLTE, right? So LTE was coined by Airtel soon after releasing of 4G. So in LTE, you can see the if you are using the data at that time you are using voice, the clarity is not good. So voice and data cannot be used alternatively. Okay, the voice and data cannot be used simultaneously in the case of LTE. Then soon after that, Geo introduced VoLTE, where the data communication and voice communication can be done simultaneously. Then people have come up with 5G. You know, 5G is now at trend. So very soon we are going to use the 5G connections. We are moving from 4G to 5G. And if you see the capacity, means if you see in a particular area, if you install 5G communication, if you enable 5G communication, and if there is a single user, the user can download 10 gigabits per second. Right? If you take a particular area in which only one user is there, then you can download 10 gigabits per second. So you see what is the how much download you can do. Right? So from one generation to another generation, our internet speed is increasing. Right? So 5G is obviously a better communication over the 4G, and 6G becomes again a better communication for 5G. So 5G is important when we need to communicate between the devices with the cloud. Okay. But the problem, as I introduced, cloud computing is very far away from these devices. They are placed in remote locations. So service time is quite more, response time is also more. So that is not a good solution. If you get a service with larger delay or a huge delay, then definitely you will not be happy. And there are many applications are also there, which is you can say it is a real-time applications like airline system applications, satellite applications. They are real-time applications in which minor delay is also not accepted. Okay, so they are delay-sensitive applications. So even if there is a delay is there, so you should think that it should not collapse the system. Okay, or you have to avoid the delay. And if minor delay is also there, that also you need to resolve it. Okay, but many systems are there in which we can tolerate the delay tolerance system. Right? Even if delay is there, that nothing is going to happen. But in delay sensitive system, if delay is happen, then it may lead to any type of loss. It will lead to catastrophic effect. It may lead to anything. So for this delay sensitive application or real time applications, so it is not practically possible to increase the delay. So in order to avoid this one, in order to avoid the latency issues, in order to avoid the bandwidth issues, in order to avoid the congestion issues, like there is a huge connections to the cloud because everybody need to push the data to the cloud. We have seen also in the last 2 days we have used the speaker has used so many IoT devices. All you are pushing to the cloud. So when congestion may occur because all are dependent on the cloud, and congestion is also happens with respect to the bandwidth. If bandwidth is low, definitely congestion will be more. So in order to avoid latency, in order to avoid the bandwidth, in order to avoid the congestion, what we are using other kind of computing paradigm which is close to the devices. That's why fog computing is coming into the picture. So rather than we depend on the cloud, we will depend on the fog for the small computation. But if in smaller computation it is not practically possible, then again we have to depend on the cloud. So here you can see, if you compare the previous architecture which talks about IoT devices to the cloud, which we call as IoT cloud architecture. Now I am showing you the fog computing architecture. So if you see what is the difference here is that we have IoT devices. So let it be our personal computer or smart vehicle or smart traffic monitoring system, smart surveillance or smartphone. These are not directly connected to the cloud. Okay, because if they directly connect to the cloud, it may lead to latency issues, bandwidth issues, or congestion. So in between these IoT devices or sensors, or you can say actuators, in between these IoT devices and this cloud, what we have, we introduced another layer that is called as fog layer. So fog computing is a hierarchical distributed infrastructure. It is completely distributed. Okay, it is completely distributed one. It is not placed in a single location, and you can see here there is a hierarchy. Hierarchy means one after another. You can say, right, one just like a tree-like structure. Right? That's why we call it a hierarchical distributed infrastructure. And the main idea of fog computing is that whatever resources we have in the cloud, the smaller version of the resources should be available with these fog nodes, so that these IoT devices and sensors, if they need any computation, they can get from these fog nodes, so that latency will be reduced. As it is a distributed infrastructure, definitely uh, in this distributed infrastructure, definitely latency is reduced, right? Congestion will be also not more because it is a distributed system. Okay, and bandwidth also can be properly utilized. So the main idea of fog computing is to extend cloud services to the edge and make everything close proximity to the end user. So now, if you look into these fog nodes are having not that much power as cloud, but they have a smaller computation power, storage power. They can also able to transmit and receive the data. Like this fog node can receive the data from a personal computer or a smart vehicle and can send the data to the cloud. Or again, it can receive some data from cloud. It can again propagate that data to these vehicles or any devices, right? So they are capable of computing anything, storing something, transmitting and receiving data with other devices and the cloud. And sometimes also one fog node may help another fog node. They can exchange the resources. Okay, one fog node is integrating with another fog node to provide the services. So that is also can be possible with the fog nodes. Now, I introduced three technology in fact. One is IoT, then we have seen there is a fog, then it is cloud. Now here we are talking about fog empowered vehicular ADAS network, which is integrating two different technology. One is fog computing, another is vehicular ADAS network. But you can see this fog empowered vehicular ADAS network can be realized through these 5G connections. Without a faster communication, it is not possible to do the fog empowered vehicular network, because vehicles will communicate when they have mobility power. So it is really challenge to connect with the vehicles with the roadside units. So vehicular radar network is also having a lot of challenges, like latency is a challenge, bandwidth is also challenge, and congestion is also a challenge. So what we did in this fog empowered vehicular network, we incorporate fog computing in vehicular network, because connecting the vehicles to the cloud is again not possible, because vehicles are having mobility power. Mobility means they have movement power. Okay, so while the vehicles are moving, frequently they are changing one location to another location. Okay, so it is very difficult to connect to the cloud, because latency is the primary issue, and devices are not close to the device, these cars or vehicles, so it is practically not possible. That's why we introduced fog here rather than directly connecting these vehicles to the cloud. But the problem with these fog nodes, which we can see in this picture, we have written RSU, that is called as roadside unit. SPN is the high power node. Okay, so RSUs are connecting with high power node. High power nodes are connected with centralized unit. and centralized unit is connected to the cloud through internet. So each fog node, which we treat here, the high power node and RSUs are as a fog nodes. These are treated as a fog node. Here you can see there is two RSUs and they are connected to the high power node. Here also there is two RSUs, they are connected to the high power node. Okay. So every fog nodes, whether it is a RSU or high power node, they have limited storage and computation capability. They don't have enough capability. That's why I told you whatever resources you will see here, there is a bigger resources or massive amount of resources available in the cloud. But you can see there are many tasks is there or many applications are there where we need smaller computation. We don't need bigger computation. So whether you need a smaller computation or bigger computation, in every case you dependent on what? These devices. Okay. Any type of communication, you device in the devices, right? So now you dependent on the fog devices, but earlier everything is pushed to the cloud. If you need a bigger computation, you go to the cloud. But if you need a smaller computation, so there is no need to go to the cloud. So that is the reason why fog node is or fog computing is introduced in between the vehicle and cloud. So every vehicle, as these vehicles are smart vehicle, so they have one unit that is called as on-board unit. Okay, every vehicle is having an on-board unit. What is the role of on-board unit? The role of on-board unit is to provide computation, storage, or you can say we need computation, storage, bandwidth. We have radar, we have cameras in the on-board unit, right? And that on-board unit can help us to connect with the RSUs, and generally whenever a vehicle is entering to a particular network, so the vehicle is sending some kind of signal, we call that the beam signal. So these signals is captured by the nearest RSU unit, and RSU units can execute some task in the vehicle, or if there is any requirement the vehicle is submitting, that can be given to the RSUs. Okay. So many things can be done by the help of these vehicles. Vehicle may require services or vehicle can provide the services because as it is a smart devices, it is capable to do computation. So many researchers also suggested that each vehicle, what you are seeing in this network, can also able to host a particular virtual machine. So they can host a virtual machines. So through these virtual machines, we can execute some task. So a client is making a request to cloud. Cloud can connect to the centralized unit. Centralized unit can balance the load and send to appropriate HPN or RSU. And RSU can execute the things in the vehicle and return the result to again cloud. In that way, vehicles can be utilized as a resources. For example, if you go for parking lot, or you go for a parking lot of a airport or a railway station, so many vehicles are in idle state. They are not using. So if these vehicle owners give consent to use their vehicles, okay, they will in return they will get some credit. So definitely they are going to use the resources. So by taking the resources like this, then we can form a instant cloud, right, or a movable cloud. So this is the Ad-Hoc cloud, but later point of time you can change the location. You can do another cloud. So the cloud can be formed on the fly, right? So onboard unit is helping us to create the virtual machines and provide the resources. Now coming to the device association technique. So there are three device association technique. Okay, three device association technique you can see. What is one is called as a signal aware, another is called as content aware, another is called capacity aware. Okay, so the smart vehicles can establish the connection with the fog node in the fog empowered vehicular network using the device association technique. So in the previous slide, you can see these are the vehicles, right? These vehicles are connecting with RSUs or with high power nodes through the device association techniques. So device association technique helps us to establish a particular connection between the cars or vehicles and the roadside infrastructure. So this device association technique can be categorized into three parts. One is signal aware technique, another is content aware technique, another is capacity aware technique. For example, if you go for signal-aware technique takes care of the things by considering signal to interference plus noise ratio quality. Okay, we look into SINR quality. For example, SINR quality is good. Suppose you are present in a location where you are reachable to two different fog nodes. Then you will check the SINR quality. Based on SINR quality, you can connect to one of the fog nodes. It is also true, like whenever we are traveling, we may present in a location where there is a coverage of multiple nodes, right, or multiple mobile towers. Nodes means mobile towers. So in that case, what happens? You will connect to a particular mobile tower where your signal strength is better, right? Similarly, there is another type of technique you can see that is called as content-aware technique. In content-aware technique, you can look into the favorite content. Like even if you are reachable to two different tower, but your content is available in one of the tower. Okay, you are reachable to only one tower. You are reachable to more than one tower, but you are connecting to one particular tower based on your content. Because if you need suppose computation in a fog node, let's say computation is not available, then it is not possible to connect with that particular fog node. Even if you connect, you will not get your service. That's why based on your type of requirement, you can connect to a particular mobile tower. Similarly, there is another technique that is called as capacity aware technique. Okay. Here we look into different resources, whether computation is available or not, storage is available or not. Okay. By looking into these resources availability in the fog node, you can do it. For example, if you look into here, there is a fog node here. If a vehicle is available in this particular range, then the vehicle can download the data at a speed of 10 Mbps. Okay, the vehicle can download the data in a speed of 10 Mbps. But when a vehicle is away from this fog node, okay, consider this particular region where the vehicle can download at a speed of 7 Mbps. Right. Similarly, if you are present in this particular if you present in this particular region, then it is also connecting with 7 Mbps. Means you can download at the speed of 7 Mbps. When you are again away, further away, then you can download at a speed of 5 Mbps here and 5 Mbps here, right? So this is your 10 Mbps zone. These two are 7 Mbps zone, and these are 5 Mbps zone. And we are taking here. These are different time slots. Like you can consider this is the time slot 1, time slot 2, time slot 3, up to time slot 7. So I am showing you different time slots. For example, these numbers indicate the vehicles, right? Like a vehicle entered in the network. This is the vehicle number 1. Then when the vehicle entered this particular network, at time t is equal to 1, you observe that it is available in 5 Mbps zone. And when you observe it for the second time at t is equal to 2, it is available in 10 Mbps zone. Right. So it is migrating from 5 Mbps to 10 Mbps zone within this time slot. Right. Maybe this vehicle is a very fast vehicle. Its mobility is very high. That's why it is moving in a very faster rate. So t is equal to 1, it is available here. T is equal to 2, it is available here. T is equal to 3, it is again in the 5 Mbps zone. And t is equal to 4 case, the vehicle is outside the fog. But when you see another vehicle, that is vehicle number 2, okay, another vehicle, that is vehicle number 2, vehicle 2 is entering to the network, so it is in the 5 Mbps zone, then it is in the 7 Mbps zone, then it is 10 Mbps zone, then again 7 Mbps zone, then again 5 Mbps zone, then it is out of the range of the fog nodes, right? So it is moving in a slower rate. If you compare vehicle 2 and vehicle 1, obviously vehicle 2 is moving very slower in comparison to the vehicle 1. Similarly, when you say t is equal to 3, the vehicle is you can say similar to our vehicle 2, but it has entered at t is equal to 3 and exit at t is equal to 8. So this picture shows that there is only one fog node which you consider either a RSU or a high power node, and there are 3 vehicles where vehicle 2 and 3 their speed is almost same,
but vehicle 1 is moving in a very faster way. And we observe these vehicles from t is equal to 1 to t is equal to 7. Now, the problem is the problem which we want to address with respect to this illustration is that every vehicle has some requirement. Okay, they want to download something. Right, they want to download. Let's say whenever we are traveling somewhere, we are downloading a movie, or we are watching a YouTube video, or we are watching our Facebook video, or we are sending a message in WhatsApp. So in that case, we request some size, some amount, right? Or you download a particular video. There is a particular size. So every vehicle has some requirement. Like vehicle one, if you look here, vehicle one requests 25 MB, where vehicle two requests 22 MB, and vehicle 3 requests 30 MB. So their requirement is different. Vehicle 1 requirement is different, vehicle 2 requirement is different, vehicle 3 requirement is different. Like somebody can watch the YouTube video at a speed of at a 1080p. Okay, somebody can watch the same video in 720p. Suppose somebody is having poor internet, and that person can watch in 144p, right? Again, these vehicle owners, as they request some content or request some uh, request, they want some content to be downloaded, they are ready to pay. So the cost to the vehicle one is going to ready to pay is 15 per MB, and vehicle two is ready to pay 35 per MB. Vehicle three is ready to pay 5 per MB. So their content wise also they have different requirement. Cost they ready to pay also, that is also different. But as you can see in this one, at a time you can in each and every time slot you can provide the resources to only one vehicle. Right? You cannot solve multiple vehicles in the same time slot. For example, if I take t is equal to 1, at a t is equal to 1, you can see here. Okay, so at t is equal to 1, how many vehicles are there? There is exactly one vehicle. So this one indicates there is a vehicle, because vehicle 2 and vehicle 3, okay, they have not arrived till now, right? So there is only one vehicle. So if there is only one vehicle, so obviously there is no competitor of vehicle 1. So vehicle 1 is only going to get the services, right? So vehicle 1, but the vehicle 1 can download only 5 MB here. It has requested 25 MB, but it can download only 5 MB. And if it is downloading 5 MB, how much it is going to pay? 15 into 5. So it is going to pay only 75. Okay. When you have multiple vehicles, you will look into these calculations, but there is only one vehicle. So obviously, vehicle 1 is only going to get 5 MB and it has to pay 75. So as a provider end, if you solve a particular problem, your objective is to maximize the revenue. You assign the resource in such a manner that you will get maximum revenue. That is the objective of this particular problem. If you develop a algorithm where you will get in these 7 time slots, you will get maximum revenue. Definitely, your approach is better than the existing approach, right? So I hope you understood that why the cost is 75. This is 5 MB you can download at a cost of 15 per MB. So 5 into 15 means you can get 75. Now, if you go for scenario 2, in scenario 2, how many vehicles are there? Can anybody tell? How many vehicles are there here? Scenario 2?
Two vehicles.
Two vehicles. One is vehicle number 2, another is vehicle number 1. Right? But I told you, at a particular time slot, we can provide the services to only one vehicle. So as a provider end, what you will see? As a provider end, you will see where you will get maximum profit, right? So if you look into vehicle number 2, okay, vehicle number 2 case, we can download 5 Mbps. But how much cost vehicle 2 has to pay? It has to pay 35 per MB. So 5 into 35. 5 into 35 is 175. If you accept the request of vehicle 2, then vehicle 2 is going to pay you 175. But if you take vehicle 1, vehicle 1 speed is what? Vehicle 1 speed is it can download 10 Mbps. Right? In this zone, it can download 10 Mbps, but it has to pay 15 per MB. So 15 into 10. So the revenue which you can get, that is only 150. So to whom will provide the service? Vehicle 2 or vehicle 1?
Vehicle 2.
Vehicle 2, because we are getting maximum revenue in the case of vehicle 2. And another interesting thing you can see here, in vehicle 2 case, which is away from the fog nodes, right, or RSU, still it is getting service. So not necessary whenever you are close to a tower you will get a service. How much you are going to pay, based on that you can decide whether vehicle 1 is going to get the service or vehicle 2 is going to have service. Now, if you go for the t is equal to 3 situation, so here all the 3 vehicles are there. Vehicle 1 is at the end of the zone and it is going to reach outside this fog node, where vehicle 3 is entering and vehicle 2 is in the 7 Mbps zone. So vehicle 3 can download 5 Mbps, vehicle 2 can download 7 Mbps, vehicle 1 can download 5 Mbps. So vehicle 3 case, if you calculate, it is 5 Mbps into 5. So revenue will get is 25. And vehicle 2 case, you will see 7 into 35. So you will get a revenue of 245. And vehicle 1 case, you will get a revenue of 5 into 15, so 75. So obviously, the highest one is 245. So vehicle 2 is going to get the service. So if you remember, in the first slot we have given services to t is equal to 1. So till now, vehicle 1 got 5 MB. T is equal to 2 case, we have given services to vehicle 2. T is equal to 3 case also, we are getting maximum revenue, right? Maximum revenue. So we are giving services to vehicle 2 only. So here we are giving 5 MB, here we are giving 7 MB. So 5 plus 7, so it is 12 MB. Till now we reached up to 12 MB. But what is the requirement for vehicle 2? It is asking you 22 MB. So up to 22 MB we have to proceed. So in the scenario 3 case, we have seen that we have given vehicle 2 because the total revenue which we expect is, we can get it is 245, which is quite more in comparison to vehicle 1 and vehicle 3. Now, if you go for scenario 4, in scenario 4, vehicle 1 is now out of order. So vehicle 1 got only 5 MB out of 25 MB. So it's if you look into the quality of the particular video, it is very poor, right? Out of 25 MB is its desired requirement, but we can able to only provide 5 MB. Okay. Now, if you go for t is equal to 4, there is 2 vehicles. One is vehicle number 3, another is vehicle number 2. Vehicle number 3 case, we can download 7 MB. Okay, so 7 into 5, so it is 35. But vehicle 2 case, we can download 10 Mbps because it is in 10 Mbps zone, right? And what is the cost vehicle 2 is going to pay? That is 35. So 35 into 10 is 350. So maximum revenue we are getting in which case? We are getting maximum revenue in the case of vehicle 2. So vehicle 2 got resources at t is equal to 2, which is 5 MB. Vehicle 2 got services in t is equal to 3, that is 7 MB. Together it is 12. Vehicle 2 is again got service here. Its size is 10 MB. So 12 plus 10 is 22 MB. Now its requirement is satisfied. So vehicle 2 got requirement is satisfied at t is equal to 4. So even if at t is equal to 5, t is equal to 6, vehicle 2 is available, it is not going to get the service. Okay. As your request is fulfilled and new request is not reached till now, so t is equal to 5 case, t is equal to 6 case, services will not be provided to our vehicle number 2. So only, although 2 vehicles are available and t is equal to 5 and t is equal to 6, only 3 is going to get the service and t is equal to 5, t is equal to 6, and t is equal to 7. So requirement of vehicle 2 is satisfied. Now scenario 5, although two vehicles are there, as I said, we are going to provide to only vehicle number 3. So vehicle number 3 can download at a speed of 10 Mbps with a cost of 5. So 10 into 5, 50. Okay. So vehicle 3 got 10 MB till now. When we go for scenario 6 case, vehicle number 3 is there, vehicle number is 2 is there, but 2's requirement is already satisfied. So what we will do? We will go for vehicle number 3. It can download 7 Mbps at a cost of 5. So 7 into 5, that is 35. So vehicle 3 got 17 MB out of 30 MB. Now at t is equal to 7, only vehicle 3 is there. Vehicle 2 is now outside the hog node. So vehicle 3 downloads 5 Mbps at a cost of 5 per MB. So 5 into 5, that is 25. Okay, so it is 22 MB. So in this calculation, what we have seen? We have seen vehicle 1 is getting 5 out of 25 MB. Vehicle 2 is getting 22 out of 22 MB. So its requirement is satisfied. Vehicle 3 is getting 22 MB out of 30 MB. So if you calculate total revenue, you will get 5 into 15. Okay, that is 75. 5 into 25, that is, sorry, 5 into 15, that is 75. Next, vehicle 2 case, we are getting 22. 22 into 35. How much you will get? 22 into 35. Can anybody calculate and tell? 22 into 35. I think you will get 770. Okay. And vehicle 3 case, you are getting 22 MB into 5. So you will get 110. So 75 plus 770 plus 110. Okay. So I think it is coming as 955. So total revenue you will get in this case, it is 955. This much you can do. Okay, this much revenue you can generate in these 7 time slots. Now, what we have to see? We have to devise a new algorithm. Okay, we have to develop a new algorithm where you can get revenue is greater than 955. You can do it, then obviously you will. This is considered as the best algorithm, right? But before that, in order to be familiar, I am showing you another example using this algorithm so that you will feel comfortable before I am telling you another solution. Okay, so now here I am showing you another example. So in which we have 2 Mbps to 5 Mbps zone. So you can see a fog node is placed in the 5 Mbps zone. And if you are away from this 5 Mbps zone, you have a 4 Mbps zone in both sides. Again, if you again far away from 4 Mbps zone, you have a 3 Mbps zone. And if you are further away, then you are in a 2 Mbps zone. You have 9 time instances, that is t is equal to 1 to t is equal to 9. Okay, but we are considering only 3 vehicles here. Like previous case, we are considering 3 vehicles. And you can see vehicle 1 is considered as the fastest vehicle. Okay, vehicle 2 is considered is little bit slower in comparison to vehicle 1. Vehicle 3 is much slower in comparison to vehicle 2 and vehicle 1. Here we assume that vehicle 1 request for 8 MB, vehicle 2 request for 10 MB, and vehicle 3 request for 22 MB. And the cost that vehicle 1 is going to pay, it is 10 per MB. Vehicle 2 has to pay 30 per MB. Vehicle 3 has to pay 5 per MB. Okay. This situation you can create your own if you want to develop a new algorithm and compare with this RRS algorithm or any other algorithm. Okay, so let us see how to solve this problem. This is another situation where you can apply RSU based resource scheduling. So at t is equal to 1, you can see the vehicle 1 is the only vehicle that is available in our system. and it is available in 3 Mbps zone, and it is ready to pay 10 per MB. So total revenue we can generate at t is equal to 1, that is 3 into 10, that is 30. Right? So vehicle 1 can download uh, 3 Mbps, okay, with a cost of 30. Right? Per MB it has to pay 10, so it is 30. But when you come t is equal to 2, two vehicles are available. One is V2, another is V1. One is V2, another is V1. V1 is available in 5 Mbps zone. V2 is available in 2 Mbps zone. V1 is ready to pay 10 per MB. So 5 Mbps means it is 50 per MB. But V2 case, it is in 2 Mbps zone. But per MB it is ready to give 30 per MB. So 2 into 30 means you will get 60. Right? So total revenue you are getting in the case of vehicle 2, it is 60. And vehicle 1 case you are getting 50. So obviously you will choose the maximum one. Right or not? So vehicle 2 is getting the service. Okay, although again you can see here, although V1 is close to the RSU or HPU or the fog node, still it is not getting service. Okay, but vehicle 2, although it is very far away because it is paying more, so revenue wise we are selecting the vehicle. So definitely this total revenue is we are getting more. So we are selecting vehicle V2. Now a complex situation you can see when t is equal to 3. Okay, t is equal to 3. How many vehicles are there? V3 is there, V2 is there, V1 is there. So V1 in 3 Mbps zone. So 3 into 10, right? 3 into 10, you will get 30. In this case, V2 case, it is 10, 30 per MB, but it can download 4 Mbps. Okay, so V2 case, it is 4 into 30, 4 Mbps it can download at a cost of 30 per MB. So it is 120. When t is equal to 3 case, again another vehicle is there here. V3 is entering into the system. So it is in 2 Mbps zone. So price we can provide that is ready to provide. It is 5 per MB. So it is 2 Mbps but 5 per MB. So it is 10. Out of these three vehicles, you are getting maximum total revenue in the case of vehicle 2. That's why vehicle 2 is going to get the service. So till now, if you see t is equal to 1, we got V1, so V1 got 3 MB. T2 case, V2 got service, so 2 MB. T3 case, in this case, particular case, again V2 got the service of 4 MB. So 2 plus 4 it is 6. So vehicle 1 it is 3 MB and vehicle 2 it is 6 MB. Now let us see t is equal to 4 case. T is equal to 4 case, what we have? V3 is present in 3 Mbps zone. V2 is available in 4 Mbps zone. Right? V3 is available in 3 Mbps zone. V2 is available in 4 Mbps zone. So it is 4 into 30, that is 120. If you talk about V3, it is 3 into 5, that is 15. So obviously, you got better revenue in the case of V2. So we are adding another 4 MB. So V2 got service at t is equal to 2, t is equal to 3, and t is equal to 4. So it is 10 MB. So our requirement is satisfied. Our requirement is full play satisfied. Okay. But vehicle 3 is unable to get the service, right? If vehicle 2 is getting, vehicle 3 will not get, because in each and every time slot, only one vehicle can get a service. Okay, so now t is equal to 4, we have given to vehicle number 2. T is equal to 5, and you can also see in this case the requirement of vehicle 2 is satisfied. Vehicle 2 requirement is 10. Here t equal to 2, it got 2. Here it is 4. Here it is 4. So 2 plus 4 means its requirement is satisfied. So in next to t is equal to 4, even if the V2 is available, we will not going to consider it. Like at t is equal to 5, you can see vehicle number 3 is there and vehicle number 2 is there. Vehicle number 3 is there, vehicle number 2 is there. But
Vehicle 2 will not participate because its requirement is satisfied. So you have only one vehicle, that is B3. It can download 4 Mbps with a cost of 5 per Mbps. So total revenue generated, it is 20. Okay, so it is 4 MB we are getting. So it is getting 4 MB and it has to pay 20. Now at t is equal to 6, what you have? Only one vehicle is there, that is B3. It is available in 5 Mbps zone. So 5 into 5, you will get 25. And t is equal to 7. It is available, V3 is available in 4 Mbps zone. At 4 Mbps zone, it can download 4 Mbps with a cost of 5 per MB. So again, it is 20. T is equal to 8. It is in 3 Mbps zone and with a cost of 5 per MB. So 3 into 5, it is 15. And T is equal to 9 case. T is equal to 9 case, it can download 2 MB at a cost of 5 per MB. So total revenue is 10. So now together, how much it has downloaded? Vehicle 3 has downloaded 18 MB. Vehicle 2 has downloaded 10 MB and its requirement is satisfied. Vehicle 1 downloaded 3 MB and its requirement is not satisfied. Okay. Vehicle 1's requirement is partially satisfied. Vehicle 3's requirement is partially satisfied, but vehicle 2 is fully satisfied. So can anybody calculate what is the total revenue here? Can anybody calculate? So vehicle 1 case 3 MB, so 3 into 10, so you will get 30. Vehicle 2 case 10 for 10 MB, right? 10 MB with a cost of 30 per MB, so you will get 300, right? So vehicle 3 case, you can download 18 MB at a cost of 5 per MB, so it is 90. So it is 420. So the cost you will get by applying this RRS algorithm in this situation, it is 420. But in the previous example, we got 955, but that is a different situation. In this situation, we got 420. So if you can develop a particular algorithm in which the cost is greater than 420, definitely that is appreciable, right? You can develop an algorithm where the total revenue of the provider is increased beyond 420, definitely increased to more than 420, then definitely we are going to accept that particular solution. Okay, so grand total revenue we got it is 420. Now, in order to improve this algorithm, we have developed a algorithm. In fact, it is a part of one of the PhD work of my student, in which we developed this revenue-based service management. That is called as RBSM, revenue-based service management. So I am taking the second situation. Similarly, later point of time as a assignment, what you can do, you can apply this RBSM algorithm to the first situation. Okay. In some situation, you may get equal result also. Right? If you apply into the first situation, maybe in some situation like first case, you may get same value also. Okay, but you have to ensure that whatever cases you have taken in which the proposed algorithm is better in comparison to the existing algorithm. So here we consider the same set of vehicles, same reachability from 2 Mbps to 5 Mbps for the fog nodes. However, the order in which we are processing, it is slightly different. For example, here we order these vehicles. We have 3 vehicles, right? Vehicle 1, vehicle 2 and vehicle 3. So we order these vehicles based on their price. For example, if you see vehicle 1, the cost is 10 per MB. Vehicle 2, the cost is 30 per MB. Vehicle 3 case, it is 5 per MB. So I have ordered them. Ordered them means vehicle 2 is paying more. So we keep vehicle 2 first. Vehicle 1 is paying the second highest one. So it is 10 per MB. So we keep vehicle 1 after vehicle 2. And we put vehicle 3 at the end because it is giving less price. So its priority, you can say, it is very less. So first change what we did here,
we order the vehicles in the non-increasing order of the price. That is vehicle 2, followed by vehicle 1, followed by vehicle 3. Now what we will do? Now not only this one, another contribution is that instead of taking t is equal to 1 to you can say t is equal to 9. If I take a static scenario, this is my static scenario, I can start with leaving of a particular vehicle to arriving of a particular vehicle. So earlier we are calculating arriving of a vehicle to departure of a particular vehicle, but here we are calculating departure of a vehicle to arriving of a particular vehicle, and we will give priority to vehicle 2. Okay, once vehicle 2 is completed, then only we will go for vehicle 1, and once vehicle 2, vehicle 1 is completed, then only we can go for vehicle 3. So as you can see, vehicle 2 case, vehicle 2 is available in which zone? It is available at t is equal to 5. It is available at t is equal to 4. Available at t is equal to 3. Available also t is equal to 2. So I told you departure of a vehicle to the arrival of a vehicle we are going to take. So if I take this one, how much I can download? I can download 2 Mbps. For this vehicle case, what I can download? How much I can download? 4 Mbps. For this vehicle case, we can download 4 Mbps. Again, in this case, we can download 2 Mbps, right? But what is the requirement? The requirement for vehicle 2 is only 10 MB. So if you download 2 here, 4 here, another 4 here, so your job is satisfied. So there is no need to take this particular slot. Okay. So vehicle 2 is given the time slot t is equal to 5, t is equal to 4, t is equal to 3. Okay. And how much revenue it can generate? So it is 2, 4 and 4. So total it is 10. How much it is ready to pay? 30 per annum. So total revenue which we can generate here, it is 300, because we have downloaded 10 MB at a cost of 30 per MB. So total revenue generated from vehicle 2, it is 300. Now, if you go for the next vehicle, now vehicle 2 is completely satisfied. Okay. Vehicle 2 requirement is satisfied. One vehicle's requirement is satisfied. So we have to look into other 2 vehicles, that is vehicle 1 and vehicle 3. So, but you can see in vehicle 2 case, t is equal to 3 is there. T is equal to 3, t equal to 2, t equal to 1. It is available in these 3 time zones, right? Or you can say these 3 time instance. T is equal to 3, it is available. T is equal to 2, it is available. T is equal to 1, it is available, right or no? So out of these slots, in the previous slide, we have seen vehicle 2 has already taken t is equal to 3 slot. So we know in each and every time slot only one vehicle can be served. So even if these 3 slots are there, t is equal to 3 slot is strike term, because it is already given to vehicle 2. Okay, you can already t is equal to 3 is already given to another vehicle. So we strike out it. So we can only give t is equal to 2 and t is equal to 1 to vehicle 1. Okay. So it can download 5 Mbps here, 3 Mbps here. Here we can download 5 Mbps, here we can download 3 Mbps. So total, the vehicle 1 can download 8 Mbps at a cost of 10 per MB. Okay, so total revenue is 80. Okay, we got total revenue is 80. Okay. Similarly, if you go for the last vehicle, vehicle 3. Vehicle 3 arrived to the system at t is equal to 3, and it is leaving the network after t is equal to 9. So we have time instance from t is equal to 9 to t is equal to 3. But you know t is equal to 3, 4, 5. It is already assigned to vehicle 2. So these options are not available now. So you can give option only time instance, that is t is equal to 6, 7, 8 and 9. 6, 7, 8, 9 only we can solve. Right? 6, 7, 8, 9. How much we can download? We can download 5 Mbps, 4 Mbps, 3 Mbps, 2 Mbps in the reverse order. So it is 5 plus 4 plus 5. So I think it is 14 MB. What is its requirement? Its requirement is 22 MB. So we cannot fulfill 22 MB, but we can download how much? 14 with a cost of 5 per MB. So 14 into 5 means the total revenue is 70. Okay. So if you see a overall calculation, vehicle 2 requirement is fully satisfied. So it is 10. It is asking 10 MB with a cost of 30 per MB. So it is 300. Right. Vehicle 1 request 8 MB, but we can provide we can provide 8 MB. Vehicle 1 case we can provide 8 MB, right? 3 plus 5 it is 8. So, but at a cost of 10 per MB, so we will get a revenue of 50 for vehicle 1. In vehicle 3 case, its requirement is 22 MB. Okay, its requirement is 22 MB, but it can get only 18 MB at a cost of 15 per 5 per MB. So 18 into 5 is it is 90. So you will get I think 14 per MB into 5. Okay, sorry, you will get 70. How much we got? I got 14 MB or 14 per MB. Right, there is 14 per MB. 14 into 5, that you will get 70. So total revenue, if you see in this particular case, you will get 450. Right, vehicle 1 case you are getting 80. Vehicle 1 case it is 80. Vehicle 2 case it is 300. Vehicle 3 case it is 70. So total revenue we got is 450. But if you remember, in the case of RRS algorithm, we got total revenue is 420. So we have improved this RRS algorithm in comparison to the RBSM algorithm. Is it clear why this total revenue is 450? Yeah, if you have any question, you can ask. Yeah, am I audible? Can anybody respond? Am I audible?
Yes.
Yeah. So you can see there is a improvement over the previous algorithm where we got 420. In this case, we got 450. So revenue is increased by 30. Okay, in the case of RBS. But you can see you can extend this particular problem by considering multiple requests per vehicle. So we have considered only one request per vehicle, right? But if you consider multiple requests, and you can formulate a new problem, and you can suggest the solution. That is one kind of improvement. Another is you can also, as I said, capacity aware. In capacity aware, we look into network bandwidth. We consider about the storage. We consider about computation. That also you need to consider various factors, and you have to see that in which zone, what are the resources that is available. So based on that also you can decide which formula is more appropriate in a particular situation, right? Based on that you can also implement this particular algorithm. Okay, we'll stop here. We'll take a break of 10-15 minutes. So we'll start at 5:45.